Hello, my name is Hunter Johnston and I am presenting on our lab about combustion dynamics in a Reiche tube. The Reiche tube was invented by Peter Reiche and it is an example of a pulse combustor, which a pulse combustor is a combustor that features combustion that occurs under oscillating conditions of pressure, velocity, and heat release of the combustion gases in the tube. The Reiche tube, as I said, is an example of a pulse combustor, and it is a long vertical tube that is open at both ends with a heat source located approximately 1/4 of the length of the tube, and it also, and here you can see in the picture that the wire mesh is the heat source of this particular Reiche tube, and the Reiche tube's main function is that it turns heat energy into sound energy, and it can be a very good example of resonance. And also, the benefits of using a pulse combustor is that the combustion intensity is increased because the fuel is mixed better because of the oscillating conditions in the tube. Also, heat transfer to the wall is increased, and also pulsations of the flow push the combustion gases out of the exhaust. And this is a very big advantage because in traditional combustors, a lot of the heat is lost in the exhaust. As mentioned on the last slide, the pressure, velocity, and heat release of the gases in the Reiche tube are oscillating with time. These conditions are actually coupled with one another. First, there is a standing pressure wave in the tube, and this represents the pressure fluctuations in the tube, and due to the heat source, the max pressure fluctuation is always at the center of the tube, and the pressure fluctuation at the ends of the tube are always zero. These pressure fluctuations induce velocity fluctuations in the tube, and the velocity fluctuations have max amplitudes at the end of the tube and have a value of 0 at the middle of the tube. And these pressure and velocity wave induce oscillating heat release, induce an oscillating heat release in the tube, which in turn induce more pressure and velocity oscillations. Now to the next slide. Now for the approach and setup of the experiment. Here you can see the Reiche tube on the left, and it has a window so we can look inside the tube and see the combustion happening. And it also has a table that can move up and down, and this table has the heat source on it. And it's located at an origin of 0, which is 1/4 the length from the bottom of the tube. You can also see the 3 pressure transducers, which are all located at quarter lengths from the bottom of the tube. So the first one is at a quarter length, the second one is at a half length, and the third one is at 3/4 length from the bottom of the tube. And the pressures in the pressure transducers are determined by piezoelectric transducers, and so these turn the pressure into an output voltage, which we can then use to measure the pressure or determine the pressure at the different locations of the tube. Also, we used a photomultiplier to determine the reaction rate of the combustion, and the photomultiplier works because light emitted by the flame is due to chemioluminescence, and this chemioluminescence is roughly proportional to the reaction rate of the flame, and therefore it is proportional to the heat release of the combustion gases in the Reiche tube. And the photomultiplier uses an optical technique to detect the flame radiation. And this technique relies on the fact that the radicals in the flame are at specific wavelengths, and only these wavelengths are allowed into the photomultiplier, which transduces these values into a voltage value. And then we use that voltage value to roughly determine the reaction rate and heat release of the combustion gases in the Reiche tube. Then the theoretical resonant frequency was determined using the formula provided in the lab manual, which came out to be 94.5 Hertz. Also, the pressure voltage values recorded by the transducers were converted into decibel values using the formulae and the transducer calibration curve in the lab manual. Here the pressure and combustion data can be seen for all four positions of the burner. Note that the frequency of the case of the closed valve at 0 inches is 104 Hz, very close to the resonant frequency, and has the largest RNS voltage. It also has the highest pressure values, which makes sense because it is in resonance and is making a really loud sound. Here the relative phase angles of the pressure transducers and the photomultiplier can be seen for the case at 0 inches and a closed valve. Note the pressure transducers are relatively in phase due to resonance, and the photomultiplier is out of phase with the pressure transducers. It is also worth noting that one can tell when the tube is resonating by looking at the flame. It'll look distorted by the moving gases like the flame on the right. Concluding all this, it is worth noting that the combustion intensity at 0 inches is greater than the intensity at 2 inches, showing that a tube in resonance has a higher combustion intensity. Also, it is worth noting that the photomultiplier is out of phase with the pressure transducers, showing that the heat release and pressure oscillations feed off of each other in constructive interference.